So here are the three approaches: storage, exclusion, and drainage. And when I talked about the drained walls, I mentioned there are 5 requirements. Oops. Obviously, I didn't line this text up properly. I lined it up on the right a bit. Anyway, so leaky cladding, drainage plane or water resistant barrier, or sheathing membrane. All 3 terms are building paper. All these things are used. There needs to be a gap to allow water to flow, and you need flashings and a weep hole. And as Marley was asking, usually before you get to grade, and often every few stories. It is very common to do it every story because then it's a replicable design. Every story is the same as the one above, and you get efficiencies and reduce error. But you know, at least at grade, and then every so often. So the leaky cladding, I gave you a list. Many claddings leak. We need that drainage plane, gap, flashings, and weep holes. So then I listed for you these claddings, and this covers most of them. And I gave you an example of what a water resistive barrier or a drainage plane or equivalent would look like. This material here could be one of several product categories. These product categories describe not a function, they describe the form or material. So this is a material made out of paper impregnated with asphalt, whereas this comes in a preformed self-adhesive roll. This comes in a preformed non-adhesive, you have to mechanically attached roll, and this comes in a bucket. That's so there's like, it's not really functional, that these descriptions, it's more about the categories about what form the product takes. So the last slide I showed last Tuesday was this slide showing details, transitions, and where you need to figure out how to get the water control layer, drainage plane, flashings at transitions between materials, between components, between trades, and at changes in plane from vertical to horizontal, from north-south to east-west, etc. Those are, and we're going to come back to this drawing a little bit more. Now, just to finish off the rain control side, I had said 1, 2, 3. 3 is the drainage gap. So let's get into talking about that part of drained assemblies. So gaps are installed in many kinds of walls, and they are not all for drainage. Particularly older walls would have gaps that were acting as a capillary break. As a thermal insulation layer, when you have masonry, a 1-inch airspace can make a big difference to the thermal performance. So, but in a drained system, that gap is performing a particular function. That is to relieve any chance of hydrostatic pressure building up by just letting gravity drag the water away. If you stop gravity dragging water away, it builds up pressure. So you just let it go, and it requires very little to do that. There's a bit of research around how big the gap has to be. I'm going to say less than 1/16 of an inch because it's pretty certain it's less than 1/8 of an inch. Probably less than 1/16 of an inch. So it's quite small. And often we have many successful systems that rely on accidental gaps, meaning they're formed by 2 materials coming together, and the nature of the 2 materials is such that there will always be some gap between them. And those gaps are hard to measure because we don't intend them. But when tested, realistic gaps like that, such as corrugated sheet metal applied directly to building paper on your garden shed. They work. They work to drain water. And so those gaps are pretty small. Now, if you make the gap larger, and I would argue that in almost all cases, we're talking about more than 10 millimeter gaps. But there are cases where smaller gaps are effective. You can let air flow through those gaps, and that helps on the drying side. Some materials, but it's not always necessary. And that's why when you see a gap drawing, don't misread it. I mean, it's easy. If you're looking for 80% solutions, then you should say the gap should be more than 12 millimeters and it's a drainage and a ventilation space. But when you're hiring an engineer to make decisions, you kind of have to know more of the story. Really, you need to be knowledgeable about the cases where, yeah, we don't need a full gap. We just need enough to drain. Or we don't need ventilation in this situation, but we need it here. And so just be aware there's a fair number of systems out there that don't have large gaps because they just need a gap for drainage, or they don't need ventilation at all. One of the numbers that is often positive about the minimum size of the gap would be to prevent a water droplet that is running on the back side of the cladding being able to bridge over and touch the other side. And if it can touch the other side, then maybe it can get wicked into this other side. So how big are droplets? This droplet size number? Well, this is not an expensive thing to measure. And so, which means I've measured it, and others have as well. But you could measure it too, take a various surfaces and slowly dribble water down. Don't turn it into Niagara Falls, but a slow and steady dribble. And then you can actually measure the size of those water droplets. And 3 millimeters is already on the relative high side of how big the droplet can be, because it just wants to run down by gravity before it gets that big. And therefore, if you don't want this to happen on the right side, you need 3 millimeters plus a tolerance. And some codes and standards have decided that number is 10 millimeters. Some codes and standards have decided that number is 6 millimeters. I think there's one that's at 4.5 millimeters too. But it's not a definitive number, but it's kind of questionable why people would be very concerned about water getting to the other side of the gap, because this is exactly where you put your WRB. And the WRB is supposed to be water resistant. Why a WRB would be expected to be water resistant, I'll let you think about that yourself. So historically, people had hoped that water would run down the back side of the cladding. Trying to draw here, would run down the back side of the cladding and then leave. But in practice, that's sort of a theoretical thing that happens. In most cases, water is penetrating at gaps and joints unintentionally, but the classic ones are around balconies, air conditioning ducts, windows, doors, pipe penetrations, all that stuff. And as a consequence, water often ends up on the support structure anyway. And so if you put your water barrier there, it's going to get wet. And so being too worried about how much water jumps over the gap is probably not that helpful as a designer to worry about, because the reality is it's going to get there. And I'm just quoting a well-known researcher by the name of Dr. Lacasse from the National Research Council in Ottawa, who had done a bunch of studies and, described that even when you had an airspace, water got across somehow, somewhere. So you need a second line of defense, so some sort of water-resistant membrane. Here, that water-resistant membrane to resist that water. So in the good old days, this was the water-resistant barrier. We would use felt paper installed in shingle fashion, and it's felted paper are short, coarse fibers. Then they are run through a bath of asphalt, and the asphalt absorbs into the fibers, but there are gaps between the fibers, microscopic gaps that allow water vapor to pass through, but by the asphalt coating protects the felt, which is a paper-based product, from rapid decay, and it also renders the surface highly water repellent. So water beads up on this surface, gravity drags it down. So this has been used for over 100 years, since the 1880s, and it's pretty successful. But it does have its limits, in that if it stays too wet for too long, it will rot. And also, not all masonry provides clear gaps. So when somebody says, I want a 3 millimeter gap, more than a 3 millimeter gap behind my cladding, well, in this drawing on the right, we definitely have more than 3 millimeters. That is about a 20-some millimeter gap, but it's filled with mortar and blobs and so on because of the nature of the construction. Now, you can properly argue that the mason could do a better job, but it's really hard to police that. So the water resistive layer in this picture on the right is the aluminum foil facing on the polyisocyanurate insulation. Here's polyiso insulation. That's what I'm doing right here. There's my iso. This is my wood stud, right? So you can see, in fact, they have a double bottom plate here because they're going to pour a floor topping. And this building hasn't had any leakage problems. It's a house. It's a tall house. It's a 3-story house, but it hasn't actually had any complaints. I've been around this building for over 20 years. It's in downtown Waterloo. The picture on the left actually is a building with problems, and this is a construction photo on the right. On the left-hand side is a inspection opening. We've taken a saw, we've had a mason cut open the building, and you can see the gap here is quite small. But that said, water will run through that gap faster than you can pour a pitcher of water. The problem is that it runs down until it hits these mortar dams. And then the water has to go sideways until it can find a spot further down. And the moment it changes direction, it builds up water pressure. That's what allows the water to go sideways, right? You need to build up a pressure to create a force to push the water sideways. And when it does that pressure, suddenly nail holes, such as the nail holes created by the masonry anchoring device called a masonry tie, become potential leakage spots. It's hard to say. And so, or any other staple hole or nail hole or whatever, suddenly could leak water if you have a blockage. So this is the complicated aspects of cavities. As I mentioned, in some systems, we can actually have a pretty clear cavity, a guarantee of a cavity, such as, for example, the E7 building with the black fiber cement panels. They're relatively accurate in dimension, better than a millimeter in thickness. They can be put over a 20, 30, 40 millimeter gap, and you can leave the joints between the panels open. 9 millimeters would be a number, 12 millimeters. And so air can go in the bottom and out the top. mind you, it can go the other way, but it's more likely to go in the bottom, get heated up by the sun, and go out the top like a chimney. And we've measured this at the University of Waterloo. Several master's students have done degrees on understanding different systems and how they work. And so we've measured and shown that. In fact, we've even videoed it with smoke and mirrors to watch the flow happening behind a masonry veneer. And behind a lot of these panel claddings, you can get some pretty remarkable amount of airflow that is very helpful for drying. And the sun is an important driver, and the wind is of second importance to driving airflow. We know that from measuring. Another student measured it in Vancouver, and quite recently, maybe 5 years ago, that kind of research was repeated in Vancouver. We did this stuff 15, 20 years ago. They did it at BCIT around 2015. They did this in Sweden. And they're confirming the results, the conclusions that we have. So it's mostly sun, then wind. The gaps don't have to be super. We're the only ones who have done quarter-inch gaps to make a difference. And how do you know when you need ventilation? Yeah, well, that's a bit more of a building science question, not a building enclosure question. But the building science question we'll try and deal with a little bit when we talk about different cladding types. So some claddings need to be kept drier than others. Some claddings leak more and therefore need more drying of the cavity. And that's how you decide. So even brick can be ventilated, and you can get clearer spaces in them, but it takes a bit more effort. So you usually do it by having larger cavities. You specify 2-inch, 50 millimeter cavities, and then even with dimensional variations, you still end up with 38. And then you try hard to inspect that they don't clog them up with extra mortar. And people have built these, have measured these, and if you look at buildings around Waterloo, particularly, Cambridge has fewer high-rise brick buildings, but if you look around, you'll see vent openings at the top and drain and vent openings at the bottom. So this air inlet at the bottom, and it's one reason why Max, the comment about a fibrous baffle. See, the problem with the fibrous baffle is it will actually significantly retard airflow. Doesn't mean we don't do it. Just telling you that that is an impact of putting too small of a weep hole or plugging the weep hole with insect screens. So you have to make your choices. When we use furring strips, that's what these vertical things are called, furring strips, or strapping is another term used, S-T-R-A-P-P-I-N-G. We naturally create a gap. Now, the benefit of these furring, I think I mentioned, is that they mechanically attach this Tyvek commercial wrap to the wall. So it's not just held on with a small washer. No, it's held on with a 65 millimeter wide by continuous length piece of wood, which really anchors that membrane, even if we get 25 pound a square foot wind gusts or something like 1.2 kPa wind gusts. No problem. That furring strip will hold it. The other thing is that, remember I mentioned that if you put a nail hole through this membrane, water could leak in. Well, if you put the nail through the wood, it self-seals because the wood clamps around the nail. You can put a nail into a wooden boat when you're sailing across a lake and it won't leak. Don't pull the nail out because it might leak a little, but if you leave the nail in, actually it won't leak. And that works the same way in these buildings. Now, hydrostatic pressure won't build up because as soon as water goes through the cladding, whatever it is that's being attached here, the water will just fall right down. It'll just fall under the force of gravity. There will be no gravity pressures to drive the water in. You're doing good. Now, in this building, you'll see that there's a different product also made by DuPont, but there is a flashing that's put at the bottom of the window opening. And that's because windows leak, and we'll get into that a bit. But at the bottom of the wall, we also have flashing. The WRB, I remember I showed you, would lap over top of it, right? And water would run over the WRB onto this flashing, and the flashing is different than the WRB in that it needs to be waterproof because it's going to change direction. A pool of water will build up here, and eventually it'll run sideways and find the weep hole and find its way out. So as somebody mentioned in the take-home question discussion, it's like, well, it would help if we slope this on an angle downward because then the pool wouldn't build up, right? The water would immediately flow. That's true. It reduces the need to be waterproof, but flashings in general need to be waterproof or close to it because they're shallow enough that water builds up and it'll leak through. Also, we want to make sure that water that gets to the bottom goes out, not in. And the way we make sure it goes out is with flashings. That's not the only way, but that is the primary way we force the water to go in the direction we want to. And you'll notice this graphical detail here. I'll show you. So when you cut through the brick, you tend to hatch the brick. Depending on your graphic standards, clay brick will have a certain hatch. The mortar might have little dots in it, or it might just be open white, depending on your hatch patterns. But where you have an open vent and drain, as this system does right here, we put an X through it to indicate that it is a open joint. And that's the kind of thing that you might stick a fibrous baffle in, an insect screen in, etc. But it's where you want the water to go out, and to make sure it goes out, you use the flashings. So a lot of these membranes and flashings are made of polymeric materials. That's what this blue is, an SBS bitumen, asphalty type modified product with a facer of high density polyethylene. That's the blue bit. The blue bit gives it strength, and the asphalt black backing is gooey, which gives it its water repellency, but also when you put a nail through it, the gooiness sticks to the nail, so it reduces the amount of leakage that could occur, and it gives it enough gooiness that it'll stick to the facer so that when you make laps and joints. So in this condition of going from vertical to horizontal, these membranes are really useful because they're not very stiff. And so when the temperature changes, they will stretch a little bit to deal with expansion and contraction. Because they're adhesive, you can lap two pieces together. Whereas the steel you see right here, that piece of metal comes in lengths of only 12 feet because it's rigid steel. And it will expand and contract with temperature quite a bit in Canadian buildings. And therefore, whenever you lap two pieces of metal together, they're going to move back and forth and make it difficult to seal them in a watertight manner. However, by using the membranes that are flexible and sticky to themselves, you can solve those problems of movement. But what you can't solve is that these membranes don't look good. No one wants to really see them, and they will break down in the sun. And so what you see here is a close-up of a solution to that. They have a small chunk of metal that the membrane laps on top of and sticks to. And what you see on the outside, this is the cladding panel, right? It's a masonry finish. You see the stainless steel, and it projects out and supports itself. But almost all the water tightness is provided by this hidden membrane, which is protected from UV, but can accommodate expansion and contraction. Before they had membranes, they would have made this piece of metal go all the way back and up. And that is not as effective. It doesn't handle expansion and contraction very well because it's so strong and stiff. and it's hard to seal the joints between the different pieces of metal and still allow movement. So that's why this combo system really is solves all of those needs, and does a really good job of that. Now here we are back in this house. I showed you the picture of the blocked cavity before and the small cavity. There were other problems, much more significant problems in this house. So does anybody see what might be wrong with this house and the flashing detail that we're looking at here? Yeah.
It looks like there's no flashing under the window. They just made it so that the bricks kind of are forced underneath that windowsill.
Yeah, so, and actually, by the way, it's the same on the jamb. Those are wooden windows, and the wood is directly in contact with brick windowsills. So water will run off the window and soak into the brick, and then it wicks into the windows, which then will rot. And guess what? They do. Now, what do you mean, Marley, by doesn't go past brick?
Oh, I just meant that the flashing doesn't extend past the brick either.
Yeah, well, I think that's actually a pretty big deal. So here's the flashing, and it stops about 1.5 inches from the outside. So it delivers water, but it doesn't deliver it all the way to the outside. And you can see from this picture here that it's just filled with mortar, right? So the water's not going to really go away. Believe it or not, you can't probably see, but in that circle, every so often, and it was quite every so often, there was a fabric rope inserted, and by the way, that was a fiber whatsoever. The nylon rope actually prevents water from passing through, and it prevents air from passing through. The reason they install nylon rope, and I don't know how common this is, but it's probably in parts of the States it'll still be common. It used to be that they would use cotton rope. And the advantage of the cotton rope was that it wicked water. So water that got to it would wick to the front and evaporate. But better than that, it took only a few years and then the cotton would rot. And then you'd have an open vent hole and a weep hole. The cotton was used so that the mason couldn't block the weep hole, because you could put mortar all around it, but it wouldn't be able to be blocked because you used cotton. But then they switched to nylon because, of course, artificial materials are better. And so now in this building, they literally had no effective drainage at all. So this nylon rope blocks water from leaking out. And so it really didn't have any drainage outlet as per like doing something like this. The flashing didn't go all the way, and the weep hole wasn't actually there. So now, but there's actually something. So I think, Marley, this part actually is one of the big problems. It didn't go far enough, and it also doesn't have weep holes. But there's something that is more fundamental than all of that, which is what really caused this building problems. But Max, the rubber flashing isn't lapped. Yeah, I think this flashing isn't lapped. The building paper goes the house wrap goes behind the rubber flashing. So I just saw the text there. It just noticed it. It was there, but so that's like tucking your pants into your boots when it's raining. Any water that runs down your waterproof pants are going to go right into your boots. In this case, the water went right into their basement walls, and it was a finished basement, and so it just It was a complete mold fest. In the end, believe it or not, this house was demolished. It was so mold infested that nobody wanted to try. Nobody wanted to try and fix it. It had too bad of a reputation by the time. So, Jonathan, you can't, we can't tell from this picture that the house wrap laps into the rough opening of the window. And the short answer is it doesn't really. So they cut it about